memorize these theorems. Memorize the theorems. So basically, if I say Roll's theorem, you have to write. So memorize the theorem. So memorize means you memorize the hypothesis and you memorize the conclusion. And of course, you have to understand what each of those parts mean. And when I say mean, you need to have an algebraic understanding of what they mean, not the graph. So if let's say, for example, if you look at Roll's theorem, it says here, if function f is continuous on closed AB, what does that exactly mean now? Many students are having a problem from right here. F is continuous on AB. Okay, so what does that mean? What does that mean? F is continuous AB, so the graph will look like this. Is that what it means? Yeah, it is continuous, but that's exactly what it means. But what does he mean algebraically? Algebraically, what does it mean? And this continuity was actually defined in chapter 1 in limits. This was in chapter 1. And this chapter 1 stuff is coming up again. It is being quoted from chapter 3. So when the test covers chapter 3, it doesn't stop at chapter 3. You also have to know chapter 1. Because the definition of continuity is coming in. And that was in chapter 1. And so you need chapter 1 and chapter 2 and chapter 3, basically. You need all of them. Okay? So all of these, so essentially the concept is cumulative. What does continuous mean? What does it mean by continuous? What does it mean by saying that the function is continuous? So now let me recall the definition. What is the definition of continuous? Definition, f, function f, continuous at x equals a, if what? If, now, does anybody remember what this thing is? Is what? Is this now? The limit of is this. A. That's what that means. That means the function is continuous. F is continuous at x equals a. And this is the definition right here. So these are the kind of things you have to know. And then what is differentiable? Differentiable on AB, what does that mean now? Now, this one says the function is continuous on an interval. What does that mean? That means the function is continuous at all points on this interval. Because this is a definition of a function continuous at a point. A function is continuous at a point, and if the function is continuous at all points on an interval, then we say that the function is continuous on that interval. That's what we say. So the first thing is that this is the definition of a function being continuous at a point. So you have to know what we mean by a function being continuous at a point, and then once you know that once you know the definition of that, then we will understand what it means by saying that the function is continuous on an interval. Okay, so that's what it means. So this is actually the definition here, but now we have what we call the variation of all these definitions, which is going to make our life a little easy. And so the variation of this is actually this right here. We actually have many variations, but this is one of the major variations. It's going to be this, and then right. So in this case, let me write this. So what I'm going to do is, how about if I'm going to write it this way, and then limit, and then I'm going to write it this way, and that can be written as this right here. It can be written as lim, and then we have what? F of x, then minus f of a, and then is equal to 0. And then the limit as x is approaching what? X is approaching a. So the limit of f of x minus f of a. Note that in this case, f of a, this guy right here, is actually a constant. This is not changing. Because here the variable is x. X is a variable, a is a constant. And therefore, that f of a is not a changing value, it's a fixed value. And so if we bring this f of a to the left-hand side, that is add negative f of a to both sides, and then stick that constant inside the limit, which we can do, because that's really a constant. And so this is actually the most common form we use in a lot of textbooks. So a lot of textbooks will say function f is continuous x equals a if we have this limit equal to 0. And why? Because this one side equal to 0. All the math people, they like to write an equation or inequality where one side is 0. It's a very common thing. So that's what you have to understand. And then and the second thing is what's differentiable here. What does differentiable on AB, what does that mean? What does that mean? What does that mean? So now let me also write a definition, here again. We have already done these definitions here. Definition, a function f is differentiable if what? If it has a derivative, basically. If this, and so let me write this down. If what? If the limit of, now we have many forms here, but how about the most common form I like? Is f of x plus h. You know what? Let's write one thing. I should write this. A function f is differentiable at x equals a, at x equals a, at x equals a, and then if the limit of this, if the limit of f of a plus h, and the minus f of a over, and then what? This is h, and then basically that's what it is. This is the limit right here of this ratio. Of course, we have these other versions as well, like f of t minus f of a over t minus a. And then, so we have other versions, but this is one version. I'm trying to explain the logic here. And now, what is the limit? The h is approaching 0. H is approaching 0. If this limit exists, what happens to this limit here? If this limit exists. Yes. Exists means what? It's a real number. Real number, not infinity. It's a real number. The limit is a real number. Like the limit is 5 or 10 or half or 0.1 or square root of 2. It can be any number, but it's a real number. If that limit is a real number, then we say that the function is differentiable at x equals a. And note that limit right there, we have a notation for that. The notation, this entire notation right here, this guy right here, that is really the definition for f prime at a. And so what we can say is that this f prime at a exists. This from f of a exists. Then we say that the function is differentiable. Exists. What does exist mean? Exist means that it's a real number again. Okay? So that's what it means. Okay, so basically, when you say f is differentiable at x, f is differentiable at x equals a. That's the same thing as saying f prime at a exists. That's what it means. Okay, that's what it means. And then what else can I say? Basically, differentiable x equals a means f prime exists. What does that mean? That means f prime at a is a real number. Is a real number. It's a real number. That's what it means. So all of these mean exactly the same thing, and that's what you have to understand. Okay. And then now, if you look at the Enroll Theorem here, we have one other condition here. It says here, what does it say? It says that f of a equals f of b. Okay. So I want you to kind of understand what it means, and then there is a number. If that is the case, then now we have this. Then there exists a number. By the way, it is differentiable. If it's differentiable, that means this is a two-side. This means that the function is two-side differentiable, either from the right and left. So this means that the right limit and the left limit and and they are the same, and that is the two-sided limit here. So when you say h is approaching 0 plus, that is a regular two-sided limit, not a one-sided limit. So the two-sided limit is a stronger case. That means that both one-sided limit must what? Must exist and must be the same. So in this case, both one-sided limit must exist and what? It must exist and be the same. And same must exist and be the same. That's the part of the definition of what? Of this two-sided limit here. Okay? So, here. Okay. Any questions here? Okay, so now let's try to understand the theorem. Try to understand the theorem here. What does this theorem exactly mean? Again, here, the first is, before you prove these kind of theorems, before you prove them, you have to understand what they mean. That's the first part, okay? So if you don't understand it, you cannot really do anything with a theorem. So you have to understand the theorem. So here, what we mean is, let's say we have an interval now. Let's try to understand what it means. So what it means is we have this. And so now, let's see, the condition is that we have an A here. Let me call it A here. So we have a point here. And we have a B here somewhere. And then note that f of A must equal f of B. That means they must be at the same level. This. And then from x goes A to x goes A into x goes B, well, we have a function here. And the graph is what? The function is continuous and must be differentiable. Especially this differential means that there must be a tangent line to the curve at every point. It cannot have any sharp corners. So if I, let's say, draw a graph like this, it does not satisfy this condition. Because at that point right there, it is not differentiable. This case, not differentiable. So what is the way to actually draw a curve which satisfies all these conditions? There's not many choice. You can actually draw a curve like this. You draw a curve like this. Or maybe I'll draw another curve using a different color. How about if I use green? We can draw a curve like this. I can do that. And then it stops there. It must be all the way to the endpoints, A and B. So the function must be defined from A to B, including both endpoints A and B. Or it could be another curve. I can draw another curve. It could be like this. That. You know what? Maybe I'll draw this more carefully here. So you can actually graph like this. Oh, you know what? Let me draw this one more time. You can do that, okay? So that blue curve is also satisfies all of these three conditions here. So all three curves, the blue and the green and the red, all three of them, they satisfy all the three conditions. And so basically, I'm letting you know what kind of graph you're talking about. How, you know? So yeah. So this is the rough picture, the rough diagram. And then if that is such a case, if the hypothesis is satisfied, all of these were the hypothesis has three conditions. So Enroll Theorem, hypothesis has three conditions. The function must be continuous from A to B, closed. It must be continuous. Second, the function must be differentiable both from A and B, because at the end points we cannot really talk about differentiable because it's the end point. So it cannot be differentiable from both sides. So in a sense, at the end, it is what? It is only one side is differentiable, or it's not really differentiable. But anyway, it is differentiable at any point from A to B open. So except that end point is only differentiable from one side. Okay, but at all the other points, it is differentiable. And then the f of A is equal to f of B. So these 2 points, they have the same y value. That's what it is. So that's what it is. So if that's the case, then what is the conclusion? The conclusion says that then there exists a number there exists a number C. So what exists? There is a number C, interval number C on open interval A to B. So when you say C is less than C is on interval A to B, what we really mean is, in simple words, basically this. It's basically A is less than what? A is less than C is less than B. That's what I mean. This is another way of saying that. So T is on the interval. T is a point on the interval on open AB. What that means, C is between A and B, which means A is less than C and C is less than B. Again, C is less than A and B. And of course, we assume that A is less than B because we write the interval AB such that F prime at C is equal to 0. So now we have this assumption. F prime at C must be 0. So if you have all these conditions here, then what is the conclusion? The conclusion is that there will be a point C somewhere there exists. Now, this theorem does not tell us where that is, but there will be a C somewhere where the derivative is 0. Now, if the function f is given specifically, like if I give you fx equals x squared, or fx cubed, or fx equals sine x plus x or something, if I actually give you a specific function, then you should be able to find the C. Okay? And there are actually such problems on our textbook. Okay? So, we will find those kind of problems. So in this case, now the conclusion is that there will be a point where the derivative is actually equal to 0. Derivative 0 means this right here. So if you look at the red curve over here, there is a point right there, at that point right there, where the derivative is 0. That means at that point, we have a horizontal tangent line. Now if you look at the green, curve, yes, green curve 2, there's a point right there where the derivative is 0. But if you look at this point here, there's also a point where the derivative is 0. We get a horizontal tangent. And then over here, we have another point right here where the derivative is 0, which is this right here. So in case of the green curve, it turns out that there are three such points. 3 points where the derivative is 0. However, the Enroll Theorem guarantees that there is at least one point where the derivative is 0. That means 1 point we actually get a horizontal tangent. There might be 2 or 1 or 2 or 3, or there might be 5, or there might be 100. But the theorem guarantees that there's at least 1. 1 is guaranteed. So that's why if you look at the red curve, there's only one such point. If that is the graph what we see, and without any misleading, if that's the graph, then that's, there's only 1 point. And then now if you look at the blue curve going down the bottom, it's going down and up, and it is smooth. We don't have any corners here. In that case, what? In that case, we have this right here. There's a point right there, the bottom. It happens to be the minimum point. At that point, what is it? The derivative is actually equal to 0. So we get a horizontal tangent there. Okay, so that's how it is. So let me just erase all those tangent lines there. So that's what the theorem is. Now we have not done the proof yet, but does everyone understand what the theorem is? Do all of you understand what the hypothesis of the theorem is? And do you understand the conclusion of the theorem? Do you understand the theorem? Even though we have not talked about the proof yet, do you understand what the theorem means? Do you understand what the theorem means? Okay, so having said all that, what I'm going to do is this. I'm going to save this page, and I'm going to make clear all this now. Now let me make some comments about the proof. Now the proof is right here. And this proof actually uses a theorem called the extreme value theorem. And this extreme value theorem was actually written in what? Written in section chapter 1. Was it chapter 1? Yes. You know what? Let me see my notes here. Let me just check. Let me grab my note for chapter 1. Chapter 1. Where is the extreme value theorem? You know what? I think it's in chapter 1 somewhere. Is it chapter 1 somewhere or chapter 2 somewhere? Let me see. Oh, I think it is in chapter 1. 1 second. Let me just, yeah. I'm trying to go to my file here to look for the notes for chapter 1. 1 second. Okay, I just have to open up all these notes here and see where, and then let me figure out where these notes are. Okay, section of chapter 1. Where is the intermediate value theorem? Where is it? The intermediate value theorem. 1 second here. Let me look for it. Oh, it is somewhere. Wait, is it in chapter 1 or is it in chapter 2? Oh, yeah. Actually, I wrote this down on section 1.8. If you look at the notes, you can see, let me write this down. Notes. Notes, section of what's notes? Section 1.8. If you look at 1.8, you know, by the way, this section 1.8 is the section where we discuss continuity. But then we didn't bother to mention this theorem, but it is written. And it is written, this intermediate value theorem can be found in practically all the calculus textbooks. You grab any calculus textbook, and then if you go to the look for the term, and in the index, on the index page, you just type in what? The intermediate value theorem. When you do that, then you will find this here. So what is this intermediate value theorem? Let me just read it for you. Let me just, you know what, instead of reading this, let me just explain to you what that is. The intermediate value theorem says this. The intermediate value theorem, what does it say? The intermediate value theorem says, that if you have a, let's say, continuous curve from here to here, and let's say it is continuous. Let's say we have a curve like this. It's continuous from A to B. So the intermediate value theorem says that if we have a continuous function from A to B, remember that if, so let's this down, if f is what? Continuous on A to B, then f has an absolute max and an absolute min. Absolute max f, let me write absolute max f to show you it is referring to the f value. Function of f is an absolute min f. So we have this. So the intermediate value theorem actually it's kind of easy to understand, but this is one of the theorems which is kind of hard to prove. In general, any theorem involving continuity, it is easy to understand, but it is not hard to prove. It is easy to understand, but not easy to prove. If you're not a math major, you will never see the proof of this guy. Okay? Again, if you're a math major, then you will see the proof of this somewhere along the line in a later math course. But if you're not a math major, then you are likely to never see the proof. Okay? Only math majors will see the proof here. So that's why a little bit the proving is much more technical. Okay? So all right. So, but first I want you to, but these theorems on continuity are easy to understand. So here the key point is, in this case you have to understand and you have to know how to use it. And so we'll look at this. So if the function is continuous on closed AB here, then there must be a max and there must be a min. And if you look at this point right here, we have a min? Yep, we do. We have a min right here. At that point, it turns out to be not differentiable. But here, the function does not have to be differentiable. The function is continuous. And then we have max right here. And at that point, is it differentiable? Well, it is not clear from the diagram, from the picture, but But anyway, let's say that it is differentiable. But anyway, though, that's the point right there. So the intermediate value theorem says that if you have a continuous function on a closed interval, then there is an absolute max, and there is also an absolute min. That's what it means. Okay, so now we look at this proof here. So what we have is we have this diagram here. So let me draw the diagram again. So we have 2 points have the same value at A, B. And then we have this. Now, so by extreme value theorem for continuous functions on a closed interval, there exists a maximum and there is a minimum. So the extreme value theorem assumes that concludes that there is a max and a min. So if the function is continuous on a closed interval, then the extreme value theorem says that there must be a max and there must be a min. Now, in our case, do we have a continuous function on a closed interval? Yes, we do. We have a function which is continuous on a closed interval, so we have that assumption. We have the assumption we need for the extreme value theorem, which is right here. The function is continuous on a closed interval. That means we can apply the extreme value theorem, and that means we have a max and we have a min. So now, basically now we are going to divide this into 3 cases. Case 1, and case 2, and case 3. One of the 3 things will happen. One of the 3 things is that the max f will be greater than f of a. So when you have a point like this, let's say we have a curve like this, and then let's say we have another curve like this. How about let's say we have a curve, this one here, and then let's say how about this? Let me draw a green curve. How about if I draw a green curve? The green curve. How about this? I'm going to draw the green curve like that. And then let me draw a blue, and then let me draw also a blue curve. I think if you draw 3 curves, I think that will do. What is this? The blue curve. So it's going to be like this, and then I will come down over here. Okay, so let's say we have these 3 curves here, blue, red, and green, and all of them, they're continuous from A to B. So these endpoints right here, let's say they are A and B. So this is A, and this point right here at A, as for this point right here, and this point right here is B. And then, of course, they have the same value. So now here I have drawn 3 curves which satisfy all 3 conditions on the Enroll Theorem. Okay, everybody class, do you follow me here at this point? All of you, do you follow me?
Yes. Yes.
Okay, now, so now if you look at the blue curve, the blue curve, is it case 1 or is it case 2 or is it case 3? Which one is it? The case 1 says the maximum of the function is greater than. Okay, so let me erase this part here so that we can see things better. So it says here now if you have a function which satisfies those 3 conditions under the Enroll Theorem, then it will satisfy at least one of the cases. So we have 3 cases here. So now the thing is, case 1 says max f is bigger than f of a, and then case 2 says min f is less than f of a, and the third case is fx is constant. Okay, so now let's look at the blue curve. The blue curve, is that the case 1 or case 2 or case 3? Or does it belong to multiple cases?
Case
1, that's right. If you look at max f is definitely greater than f of a. So it is true under case 1. Now is it true under case 2 as well? Is this blue curve under case 2?
No.
Yeah, no, not really. Because if you look at case 2, if you look at the blue curve, if you look at the blue curve here, then what we do see is that the max f is what? Max f is let me write this in blue. So max f is actually is greater than f of a. That is true. But min f is actually what? Min f is equal to f of a. So note that the minimum f is not less than f of a. It's what? It's equal to f of a. At x equals a, it's actually, that's the endpoint, and it happens that that's actually the minimum point. So therefore, in this case, this blue curve only satisfies case 1. So that's case 1. Now, if you look at the red curve, what is true about this red curve? Is red curve case 1 or case 2? Or case 3? Which one is it?
Case 1 and 2.
That's right. The red curve is now under the case 1, or it could belong to case 2. Because case 1 says f of x is what? The maximum is higher than f of a, which is higher than f of a. And the minimum is actually lower than f of a. So this red curve belongs to case 1 and 2. Now how about if you look at the green curve? The green curve, the maximum occurs at the end, f of a, so that is equal to f of a. Now the key is that this is greater, not less than. So case 2, this guy is case 2. So the green curve is actually case 3. This green curve is actually case 2. This is case 2. Why is this case 2? Because in this case, max f, let me use green here. So in this case, green is what? Max f is actually equal to f of a. It's not greater. But what we do see is that min f is equal to, is actually less than f of a. We have this. Now, let me ask you this. Max f is less than f of a. Is this possible or not possible? Is max f less than f of a possible or not possible? Is that possible or not possible, class? Let me write this in red. Is max f less than f of a? Is that possible or not possible? That's possible too, right? Is it possible?
You mean the green? You mean the green one, right?
No, not the green. Any curve. Let's say, how about this? How about this? Now, let me give you an example here. Example. Let g be any function. Let g be any function. Is a max g less than f over g of let's say a possible? Do you think max g can be less than g of a? Possible or not possible?
No, I just realized it's not.
So why is this not possible? Why is it not possible? Because what was the definition of? What was the definition of? Definition of what? The function of a function g. Function g is what? G has max f at x equals what? X equals a. If what? If g of what? G of x is what? Is if g of a. Okay, if g of x is what? Is less or equal to g of what? G of a. For all x. So if you look at the definition of a max and min, this is now of course an absolute max. Has an absolute max. This is the definition of absolute max. Okay, so this is again, let me say absolute max here. So we say that the function has an absolute max at x equals a if g of a should always be higher than anybody out there. So if g of a is lower than f of a, then that's not maximum g. So just by the definition, upon the definition of maximum g cannot be less than g of a. Is that clear? So is that possible or not possible? So this is not possible. So this is not possible. What is possible is g of a, g of what? G of a is equal to g of a, or how about basically max g. So what is possible is max g is equal to g of a. Yeah, that's possible. Possible. And then max g is what? Max g is what is greater than g of a. That's possible too. But max G is less than G of A. This is impossible. Does it make sense? Because by definition of max, it must reach the highest Y value. So just according to definition, that's why we don't see we don't have a case where max F is less than FA. That means that's impossible. But it can be equal. Okay, so now what we do is, and then case 3, and then the third case is fx is constant. So if you have a function, how about if you have a, let's say, a fourth curve, which is like this, a fourth curve, I'm going to do this, but I'm almost going to get into the proof of this Enroll Theorem here, and then let's say we have, let me write this in black, and then let me draw a thick marker here, and the thick marker is over here. So let's say if you have a curve like this, which is actually a constant function, the black curve right here. So in that case, if you look at the black curve, is that under case 1 or is that case 2? The black curve, which is a horizontal segment, is that case 1 or case 2? Is max F greater than F of A? No. Max F is equal to F of A in this case. And then how about this one? Second one, is min F less than F of A? No. Min F is not F of A. Min F is actually equal to F of A. So when you have a horizontal segment like this black colored graph, this one, the max F and the min F, they're both equal to F of A. So it does not belong to case 1, it does not belong to case 2. This is the case of case 3. Fx is a constant. If case 1 and case 2 are both false, if you have any curve which does not belong to case 1 or case 2, then it must be a constant. Okay? So we have 3 cases. And then now, what is the conclusion? The conclusion is that, what is the conclusion? The conclusion is that there must be a C on the open interval AB. Oh, that changes to purple. Oh, purple is not too bad. A C on AB, then such that F comma C is equal to 0. So if in all these cases here, according to the theorem, there must be a point where the derivative is 0. I think the easiest one to prove is actually case 3. If fx is a constant, is there a point where the derivative is 0? If you have a curve like this, in black, a horizontal segment, do we have a point where the derivative is 0? Case 3?
No.
No? Actually, we do. If you pick up this point right here, what is the derivative of this to the curve at this point? Maybe I should mark it red. Can't see the purple. So let's say if I mark a point right here on this black curve, which is a horizontal segment, what is the derivative of that? What is the derivative of this curve at that point, at that red point? What is the derivative?
Is it 0?
0. If you draw any tangent line, by the way, if you have a line, let's say here, if you have a line like this, and then we pick a point, and then I pick a point here, and then I pick a point, what is the tangent line to this curve at that point? So do we ever talk about a tangent line to a line at a point? Yeah, we can, but this is kind of boring. Because when you actually look at the definition of a tangent line, the tangent line is the linear behavior of the curve at that point. But if the curve itself is a line, it's not that interesting because the graph is a line. In that case, the tangent line is the line itself. If the function is a line, if the curve is a line, so in this case, what it is if you have a curve like, and then that's the tangent point right there. If the curve is a line, and then we pick a point on that line, what is the tangent line to the curve at that point? What is that? That is going to be the line itself. In case you didn't know, it's kind of boring. So if it's a line, that line itself is a tangent line. Except you cannot get that is not the tangent line when you have a corner like this. Let's say when you have a corner like, and let's say if you have a corner like this, or we have this right here, it bends like that. And at that point, of course, we don't get a tangent line. The right tangent line, and we have left tangent line. But we don't get a two-sided tangent line at this point. But if you pick any point here or anywhere in the middle, the tangent line to that line is actually that line. It's kind of boring. Okay. So now we come back to this curve here, the black curve over here. the black curve over here, right? Here we look at this curve, we look at this part, and the red dot there. So let me kind of erase. Okay, so this one here. Let me just maybe mark with this. Draw this with red. Okay. All right. I made it right. So now you come to this black segment here, and then we pick a point. What is the derivative to the curve at that red point? This is a constant function now. What is the derivative at that point? The derivative is 0. The tangent line is the line itself, and the horizontal tangent line, the slope is 0. So therefore what? The derivative is 0. So if you look at the black curve, at every point, it's what? The derivative is 0. So for the black curve, although it says here that the mean value theorem guarantees that there's at least one point where the derivative is 0, but if it's case 3, if it's a constant function, the derivative is not 0 at 1 or 2 points. It is the derivative is 0 at all these points in the middle. So it's obvious, basically. So there really is not much to prove under case 3. So now what we do is now we look at case 1. So why don't we now look at the case 1? Case 1 is the blue curve. So we now want to look at the blue curve. Okay. So the blue curve, let's look at it. You know what? I'm almost proving this theorem here. Yeah, I told you I'm not going to prove this theorem, but I'm about to now prove the theorem. So now this is the blue curve. So now we look at the blue curve here. And so now, what is the blue curve assumption? Now let's understand what the assumption is. For case 1, what is the assumption? The assumption is that max f is greater than f of a. And we have the function is what? Is continuous on the closed interval AB. And then we have f is differentiable on open AB. And we have f of a is equal to f of b. And then we have the case assumption that we have f of a is greater than f of a. So now if I write all the assumptions to this part of the theorem, we have how many assumptions to prove case 1? How many assumptions do we have here? How many assumptions we have this here? One assumption. The first one assumption, the second assumption. And then we have the third assumption. These 3 assumptions are the assumptions for the theorem. And then now we have one more assumption. This is the case assumption. Because we are now trying to prove the theorem under case 1. So we have 4 assumptions. So you have to know exactly what the rules are. So now what is that we have to prove? We have to prove that there's a point, there's number C where the derivative is equal to 0. The derivative is 0. This is actually f prime at equals 0. The derivative is 0. So you have to show that under case 1, at some point the derivative will be 0. That's what we have to show. So now in this case, what we do is case 1. What we want to show is this. Now here we called it f of a. Did I call f of a here? You know what? I actually made a mistake here. This is, you know what? Actually, sorry, it's not a mistake. So how about this? So now what we do is, if you look at case 1 assumption says, so let me erase this here. If you look at the case 1 assumption, it says f of a, max f is greater than f of a. So obviously f of a is not the max. So in this case, let's see where the max occurs. If f of a is not the max, will there be a max? Yeah, there is a max. So there is a max. There is a max f here. So where should he say that the max is? So let's assume in this case. So we assume this is a case 1 assumption. Case 1 assumption. Assume max f is equal to f of what? C. Let's say that at C we have a max. So this is the max. This is the part which I should have written here. I kind of forgot. So this is the part we assume. So now what we assume is that at this point right here we have a maximum. We have a maximum here. Yeah, that's for sure. According to intermediate value here, we have a max. And now what we want to say is that this max right here, let's say that point right there is actually C. Let's assume we know that there's a max. Let's assume that the max is occurring at C. Now, what we are going to show is that we'll show So we can show we will show that f prime at c is actually equal to 0. And will this actually be true? And yes, it will be true. Why is it true? So now, in order to find the derivative here, f prime at c, and by the way, it does say that f is differentiable. So that means there must be a limit, there must be a derivative, and so in this case, it must be a real number. Now, if you look at this here, I wrote the two items here. I wrote the left and the right derivative. So I wrote f prime plus at c, and I wrote down f prime minus at c. Now, can somebody tell me whether this guy is bigger than 0 or less than 0? This guy here? This guy here. Do you think this right here is now f prime and c is equal to this guy, where h is approaching 0 plus? Can we conclude that this is negative or positive? What can you say about the sign of this guy? The thing which I marked in blue, that box right there, which is the f prime plus at c, this is the right derivative of f at c. Is that positive or is that negative? Of course, we assume that max f is what? Is f of c. So we assume that at c we have a maximum. Now, on that assumption, is that positive or negative? That box right there. The limit, which I boxed.
Is it negative?
Is that negative? Yeah, that is negative. Now, how do you know that that is negative?
It's maximum, so like when you go to the right, it goes down. The slope is negative.
Right. If you look at the graph here, good observation. So if you look at the graphical observation here, we are comparing this point right here, f of c, and then we are comparing that to f of c plus h. And since h is up plus here, h is up with 0 plus, we know that h is actually a plus number. That means we're comparing to this point right here. So if we compare this point right here and then compare that point right there, then which is the highest point? Of course, this f of c, this guy is the highest point. Now, even without that graph, see, note that f of c, max f is equal to f of c. So if we assume that max f is equal to f of c, that means we have maximum reaching at x equals c. That means this guy f of c is the higher value, and then this f of c plus h, well, we don't know what that is, but this is definitely less than f of c. Why? Because we have assumed that this f of c is the maximum. So we can see that this guy is actually the limit of what is the top. The numerator is actually a negative number. That's all we know. And then if you look at over here, and then if you look at the denominator, h is up with 0 plus. This guy's actually a plus number. So we actually have a limit of negative over positive. So in this case, this can only be less or equal to 0, if it exists. But we know that it cannot be positive, because it's negative over positive. But how do you know that it can be 0? Sometimes we hit that borderline, and it could be 0. It could be 0, sure. But it cannot be positive, though. So we know that the right derivative must be positive. And so now basically what that means is you have a point here and a point here. And now if you connect these 2 points here, what kind of a slope are you going to get? Of course, you'll always get a negative slope. But who knows? If it's for certain crop, we might hit the 0. We might get this. But the right derivative cannot have a positive slope. The right derivative cannot be positive, because the line will always either go flat or it will go down, because the point of the right will be either below the maximum or might approach the top point. But in any case, the right derivative cannot be positive, because this point on the right is always lower, according to the definition of max. Now, if you look at the left limit, it's the other case. If you now have a point on this side and then connect the 2 points, it is always positive. So this guy here, because f of c is the big guy, this guy is always a bigger. The small minus big is negative, but then the denominator is negative. So this bottom here is actually what? The limit of a negative over negative. So this guy is actually equal to what? 0. So we get this. So let me save this, and now let me erase some of the stuff here. Right? But now, what is the assumption? But the assumption is that, but we assumed that f prime at c exists. One of the items we produced, one of the things we assumed was that f prime at c exists. Where did we assume that? We assumed that f is differentiable on AB, where on any point between A and B. And note that point C is actually a point between A and B. So we have this assumption right here. The assumption is this guy. The assumption is this guy right here. And so f prime exists. So the question is, that means f prime at c must be a number. How can f prime at c be a number? So f prime at c must equal what? Now there's only one choice. F prime at c can only be what? Can only be 0. Why? Because the right limit is positive, and the right limit and the right derivative is positive. The right derivative is negative, and the left derivative is positive. So we know that this two-sided derivative must equal the right derivative and the left derivative, and they must be the same number. So in this case, what same number can you add? Well, this guy, one guy is less than or equal to 0, the other guy is greater than 0. So the only thing is we must have a 0. So what we have shown is that at that point where we reach the maximum, the derivative is actually equal to 0. That's what we show. And then case 2 is very similar. It's actually a reverse case where we have a minimum. In this case, we pick the minimum point, call that guy C, and we do the same thing. And then the signs will be opposite for both of these here. And then the conclusion will be this. And then the case 3 is a constant. And so for that one, it's proven. So you know what? I actually told you that I was not going to prove the Rolle's theorem, but I ended up proving the Rolle's theorem. You just have to yeah. So anyway, so you know what? This is actually the whole proof of this. You have to write this down here. You have to show this down, show this. And then this is what we will show. And we have shown right here. So we have shown case 1. This is the proof of case 1. I only prove case 1. Now case 2, the proof is very similar to case 1. In case 2, we take a minimum point right here and call that point C. That point we call x equals C, and then show that f prime at c at the minimum point, with the derivative will be 0. That's what we have to show. And in case 3, there's not much to prove. If it's not case 1 and case 2, there must be a constant. In that case, the function, the derivative is 0 at every point, so there's not much to prove there. So basically, this is basically the proof. Okay? Although I only prove for case 1, when you know what, after this class over, maybe you should try to prove case 2. Very similar, but you should be able to prove it. Okay? I'm not going to do it because it's very, very similar. Too similar. So that's that. Okay, so that is the end of the Rolle's theorem. So now what I'm going to do is, let me now clear this. So now what I would like to do is on to mean value theorem. The mean value theorem here. Okay, and this is ultimately the theorem which we are going to apply. Okay, so what is this mean value theorem? The mean value theorem says this. This time we have now mean value theorem. The function, by the way, this is kind of similar to the Rolle's theorem. Mean value theorem says the function is continuous on poles AB and it's differentiable. But note that the third condition is not there. And on the Rolle's theorem, we had f of A equals f of B. But in mean value theorem, we don't have that assumption. So in this case, what we have this. We have a point here at A. And then we have a point, how about this? Let me now use a black marker. So here we have point A at A. Why point call it A? And then we call this guy B. And you know what? This one kind of looks like it's B. So let me rewrite this. This is A. And then this point B. And then the point is over here. Is not the same as f of A. Okay? So what kind of curves do we have? Well, we could have a curve like this. Let me draw some curves. Yeah, we can have a green curve, or we can have a blue curve. Like this, or we can have a, how about a purple curve? Of course, we can also have a curve like this, going straight like this. Maybe we can have any curves. All of these curves, they satisfy the hypothesis. The function is differentiable, and it's what? And it's continuous. Oh, by the way, I didn't show you what happens if the hypothesis is not satisfied. Yeah, so maybe I'll do that maybe after this. You know what? Yeah, you know what? Let me talk about that counter case, the non-case. Let me just explain this, and then I'll get to the other case. Okay? So now here, so if you look at this one, so we have all these cases here. Now, so if you have such a curve, then what is the conclusion of the mean value theorem? The conclusion of the mean value theorem is that there exists a number c on the opening square b such that f comma c is equal to this guy right here. Now, what does that mean? What is this? This here means that there is a number c such that f comma c, that is the derivative of f at c, is equal to this guy right here. Now, what is this guy? Oh, that guy right there? That is just the slope of the line connecting the 2 points. That's the slope of that is the slope of the black line. The line segment, which is that is a segment, that is a line. That's the slope of the line connecting the 2 endpoints. That's what that is. So the derivative of f at c must be the same as the slope of the line connecting the 2 points. Okay, well, should be the slope of the line connecting the 2 endpoints like this. So what does that mean? That means there's a point somewhere. Let's say if you look at the green curve, yeah, there is a point somewhere. There's a point somewhere where the derivative is actually what? Where the derivative is actually the same as the slope of the black line. That means the tangent line must be what? Must be parallel. That's what it means. How about if you have a blue curve? Then that means there must be a point somewhere where the derivative is the same as the slope of the line connecting to 2 endpoints. That means there's a line parallel to that. Or, in this case, for blue line, a blue curve, we have actually this point, that point. We also have another point here. We have actually how many points? We actually have how many points here? We have actually 3 points. Where the tangent line is parallel to the line connecting the endpoints. And then now if you have a purple curve, then with the purple curve, then what is it? Yeah, we also have a tangent line which is parallel to the line connecting the endpoints. So we have that right there. So that's what it's saying. So no matter what the curve is, the mean value theorem says that there is a tangent line somewhere in the middle which is parallel to the line connecting the 2 endpoints. So that means there's a point somewhere at C where the derivative at that point, the derivative to the curve at that point is equal to the slope of the line connecting the 2 endpoints. So no matter how you graph, there is actually what? There is actually a curve which has that. Now, so that's what we call the mean value theorem. How about this? Let me now give you an example. Now, how about if the curve looks like this? Let's say we have a point here, and we have a point here. How about if we have a curve like this? Okay. Let me redraw this curve. Then we have a curve like this. You know what? Let me redraw this. I need to graph this more carefully here. So let's say we have a curve like this. A, B. And then if you connect the 2 points, then the line is going to look like this. Do you think we have a tangent line on this curve to the curve, which will be parallel to this line right here, this dotted line? You know what? Actually, in this case, we might. You know what? Let me graph this a little more clearly so that it is actually clear from the. So let me clear all this. I guess what I'll do is I'm going to do this. I guess it is not hard to draw something which is not. So let me draw this. No, not do that. Okay, so let me do it again. I think that will be more clear. So if you have a curve like this, now and then this is a line connecting the two endpoints. What is the conclusion? Will there be a tangent line which will be parallel to this line? And as you can see, no. If you were to, if you kind of want to draw a line like this, but obviously that is not a tangent line. So in this case, you know that C does not exist. The point where the derivative is same as the slope of the tangent line same as the line connecting the two endpoints. That C does not exist here. And why is that in this case? Because in this case, the function is not differentiable. If the function is not differentiable, it's not guaranteed. So how about this? How about if you have a blue curve? How about, let me draw another curve here. How about this curve? Now, if you look at this blue curve here, let's see what happens. Does the blue curve satisfy the hypothesis of the mean value theorem? Does the blue curve satisfy the hypothesis of the mean value theorem? In other words, this part is hypothesis. This part is hypothesis. So does the blue curve satisfy these conditions? We have two conditions. The function is continuous on closed AB, and the function is differentiable on open AB. Are the two conditions satisfied? So for this blue curve right here, does the blue curve satisfy these two conditions? Yes or no?
No.
No, it does not satisfy. Now for this blue curve, if the graph is what you see right here, is there a point C where the derivative is equal to the slope of the line connecting the two endpoints? Do we have such a point C? Is this true? Is the conclusion true? Now in this case, because hypothesis is not satisfied, there is no guarantee that the conclusion will be true. However, in this case, actually there is a point right here. There's a point right here where the derivative is what? It's actually equal to the slope of the line connecting the two endpoints. So we have such a point. Even though the hypothesis of the theorem is false. So if the hypothesis is false, does that mean that the conclusion is false? If the hypothesis is false, then the conclusion may be true or may not be true. I want you to understand this logically. But if the hypothesis is false, there is no guarantee that the conclusion will be true. In other words, the theorem itself does not apply. If hypothesis is not true, then if hypothesis is false, then theorem does not apply.
All of our food, we never go out.
It does not mean that the conclusion is false. That means the theorem does not apply. That means the conclusion may be true or false. Yeah, that's what it means. It is basically, it's going to be inconclusive. That's what it means. But if the assumption is true, then the conclusion will be true. That's what that is. Okay? So now, you know what, I guess for the mean value theorem, I'm running out of time here, so I cannot do it. So what I'll do is this. I'm going to let me just save this here, and I'm going to erase all this. Now for the mean value theorem, actually, it's how to prove this. So we will be proving this Enroll theorem to H on the closed AB, and so here we actually create a function like this. So we have a function which satisfies this and that, and now we're going to show that there is a C which satisfies that right there. So for the mean value theorem, what do we do first? We actually create a function called H. The question is, what is this H? Question is, what is this H? What is this What is the question mark? What is this h? This h right here, if you look at it, this is actually equal to f of this h of x. What is this h of x? Let me just give you a hint here. This one. This h of x. What is this h of x? H of x is equal to f of x, and then minus L of x. It's actually L of x. So what is this L of x? Let me tell you what L of x is. L of x is actually the line which connects the two endpoints. You know this line right here? Let me draw this in thick marker. This red line right, this line right here, which is passing through two endpoints. This line is actually what? This line is L of x. So this line is actually y is equal to L of x. L of x. And then what is that curve? Let's say we have a curve like this. How about we look at the green curve? How about if you look at the blue curve? The blue curve, what I'm going to do is, let's say that we have the blue curve. The blue curve is a little bit more interesting. Is the blue curve is actually going up like this. So let's say this is our function. This is the blue curve here. And so that's our blue curve here. So that blue curve, let's say that is equal to, that is what? That is y is equal to, that is equal to y of f. That's y equals f of x. So that's the blue curve. So let's say that's the blue curve. And now what is this h of x? H of x, it turns out that the h of x is this. H of x is this right here. We have the 2 points here. Oops. Let's not, let me now have a thick thin marker. Let me change my color to black. And so let me color this to red. If you look at this line here, and then this point here, and this point here. Actually, in this case, the blue curve should be up. So the difference here, what? This difference right here, that difference is actually what? It is h of x. H of x is equal to what? H of x is equal to f of x minus what? F of x minus g of x. F of x minus L of x.
Good, thanks.
F of x
Wow, it's so
minus
sunny there.
L of x.
Beautiful.
Times. Okay, this would be, could be what? That could be plus or minus. Plus or minus.
So, I just came in, so I'm...
If the graph y equals fx is higher, then h of x is positive. So that, the difference between the graph and the line, that's what this h of x is. But anyway, you know what? I'm not going to prove this. And so I will let you ask you to prove this, prove the rest of it. You have to what? You have to prove the rule. You have to apply the Enroll Theorem, and that's how it's going to be. All right, any questions here?
How much time did you say we had for each? Okay, so I'll just times...
Any questions here?
Let's see. Do you guys want to do 3 or 5 minutes?
No.
No questions?
Okay, yeah, because there's...
No.
Let me see.
You guys.
I'm
not going to go...
My desk, my line on my desk is kind of a mess here. Let me see. Let me just clear some stuff here.
Okay,
Yeah,
so
to find that the intermediate value theorem, I made a mess out of
we can do popcorn too.
this stuff.
I'll choose.
Okay, so again, I want you to study the proof of the mean value theorem. Basically, this is almost done. You have to kind of put it together, and you have to know what to do with it. But you have to apply the rules here. So this is all of this. The calculus. There's not much calculation here, but you need to know what needs to be done. So the important thing is the logical problem. What is that you have to do here? What's going on? So what is that you have to do? That's the hard part, not the calculation. There is not much calculation here. The whole thing will just take a minute or two. But the hard part is what? The hard part is. So I'm not saying that it takes 1 or 2 minutes. That is if you know what to do. If you don't know what to do, but this will take forever, and you will not be able to prove this, all right? But here, I gave you all the hints and everything. Your job is to put all these together and actually prove the mean value theorem. Again, I gave you the initial argument, and you have to know everything about the Enroll Theorem, and so you have to all put it together. That will be you have to be like an editor in a sense. Okay, so that's what you have to do. Okay, so now what I'm going to do is now this. Okay, so that's the mean value. So now let's get to the corollary. The corollaries are theorems which follows immediately from the mean value theorem. That's what we mean by the corollary to the mean value theorem. Once again, a corollary is a theorem which immediately follows from another theorem. So, that's what we call a corollary. So corollaries are theorems too. So now let's look at parts 1A, 1B, 2, and 3. We need all of these things. We actually need number 2 and number 3 when you go to the next, this chapter. That's right. We need this. And we need number 1A, and 1B when you get to the next chapter. But they are in the same thing. So that's why I want to mention this. Okay, so now let's look at the theorem. So again, we can prove all this. Maybe I'll prove 1A, and then you'll get the hang of it. Okay, so that will kind of show you how these things work. Okay, so let me first clear this. So I'm going to save the screen and then clear all this. Now let's look at example 1. Let's do example 1 here. It says here, part 1A. If f prime of x equals 0 for all x, then f of x is constant. Now, if you look at the graph here, this kind of makes sense. How can you draw a curve? How can you draw a curve where the derivative is 0 all the time? So here it says that the derivative is 0 for all x. That means the derivative is 0. The derivative is 0, that means every tangent line is a horizontal line. How can the graph be if the derivative is 0 for all x? What kind of a line what kind of a graph can you draw? This kind, how can you graph a function f of x if the derivative is 0 for all x? Can you solve such a function whose derivative is 0 all the time at every point? There's only one way to graph, right? How would the graph look like?
A horizontal line.
Right, we can only draw a horizontal line. Because as soon as we try to go up, what happens? The derivative is not going to be 0. As soon as we try to go down, the derivative cannot be 0. That is, this exists. And by the way, when it says f prime of x equals 0 for all x, this automatically assumes that f prime exists. So when you say, okay, but basically when you say, let's say, for example, if you say this, if you say, okay, so example here, if you say f prime at f prime, let's say at 2, f prime at 2 is equal to, let's say, 5. This means, okay, this means that f prime at x exists. F prime at 2 exists and f prime at 2 is equal to 5. I don't know, does that make sense? But when you say f prime of 2 is equal to something, that means that f prime exists. Well, we don't say that, but the way to understand is f prime of 2 exists, and it's 5. If it doesn't exist, it cannot be a number. So we assume that it exists. So in this case, f prime at x equals 0 for all x. That means f prime obviously exists. So how can you draw a curve where f prime exists all the time and the derivative is 0 all the time? Well, the only way is to draw a horizontal line. Because as we move on, as we move on, well, how can you draw it? We can just go, we have to go straight like this, because the derivative has to be 0 all the time, and so we end up drawing constant. So now in this case here, if that is the case, then you know what? The function must be a constant function. Now this theorem here, it looks obvious, it kind of looks trivial from the graphical standpoint of view. Graphically speaking, this makes a lot of sense. However, here we are to show algebraically. All of the proofs must be shown algebraically. Okay, how do you show this? How do we show this here? How do you show this? Okay, so f from x equals 0 for x, we get it. Okay, so this is how we show. Now, in this case, now let me do this here, proof of 1a. Okay, so what? Show f of x is a constant. Is equal to a constant. So how do you show this? So what we will show is, how about this? Left, well, left. A, not equal to B. So how about this? Let's instead of A and B, since I used A and B for all these endpoints here, let me change the letters. Let P and Q. Let P be. Let me pick two numbers P and Q, where the 2 points are not the same.
Very cool. So do you want
Where the 2 points are not the same. Now, when 2 points are not the same, now to show that this f of x is constant, what do you think I need to show? Can somebody tell me what I need to show? So right now we're in the process of showing that the f of x is constant. This is what I want to show. So to show this, you know what I did? I did this. Let P is not the same as Q. What statement do you think I need to show to prove that the functions are constant? Can you tell me? So in this case, what we will show what? We will show a claim, or we will say we will, okay. So sometimes we claim, or we show, okay, want to show. So we will show what? What does it we have to show about this P and Q so that this function is actually constant? Can you tell me what we have to show about this P and Q? This is where the logic works. Okay? So here I'm in the process of showing that f is a constant. To show that f is constant, what I did was I picked two numbers, P and Q, which are not the same. Now, what statement do you think I need to show which will show that the function is constant? And of course, P and Q, we really mean that P and Q are any two numbers. This is really any P and Q. Any P and Q. So any P and Q, the P and Q can be any two numbers which are different. Okay? And now what is it that we have to show that this function is constant? Can somebody tell me? What do you think we need to show?
Y of P equals Y of Q.
That's right. You say Y? Okay, you can say Y. In this case, we'll say just f of P is equal to what? Is equal to f of Q. This is what we're going to show. We will show this guy because because the assumption is that the derivative is 0 all the time. So so now in this case, again, or this is the same thing as saying f of what P, and then what minus f of Q is equal to 0. So this is actually a form of the statement which we want to show. And of course, we assume what we assume? We assume what? We assume f prime at f prime. We assume that f prime of x equals 0 for all x. For all x. Oops. For all x. Let me write this in blue. How about in black? Okay, you know what? The green is kind of it's kind of overlapping with the red here. But anyway, we assume that f prime of x equals 0 for all x. So now let's show that statement. So now what do I need to show? What I'm going to do is this. I'm going to do this now. What I'm going to do is now. Okay, let's start with the left hand side of the statement. Let's start with f of P, and then minus f of Q. Okay, so what is this equal to? So what I'm going to do is now, since P is not Q, what we can do is we can actually divide. So this is what we will do. This is f of P, and then minus f of Q, and then over P minus Q, and then this, and then what we want to have is, and then we want to do this, and then time, and then over this, and then times P minus Q, then times P minus Q. So what I did was I did this. I divide by P minus Q, and then I multiply by P minus Q. The question is, we started with this P minus Q. Why did I divide this by P minus Q and multiply this by P minus Q? We want to know the reason why you want to do this, because when we divide and multiply it like this, then now, you know what? I want to see the mean value theorem here. The mean value theorem, let me, do a little bit, how about this? I'll just, I'm going to do this here. I'm going to adjust this, and now what I'm going to do is I'm going to erase this part right here. This part, we don't need it, so let me erase, so that we can see the mean value theorem. Now, if you look at the mean value theorem, if you look at the mean value theorem, the mean value conclusion is that we have this conclusion right here. The conclusion of the mean value theorem is this guy right here. And if you look at this equation right here, the final equation here, we see this shape right here. So that's what we need. Because in this case, we want to apply the mean value theorem. So now let's say we have a function here, f prime of x equals 0 for our x right here. Now this function right here, does this satisfy the hypothesis of mean value theorem? Does this function f satisfy the mean value theorem? If f prime of x equals 0 for all x right here, then does this function f satisfy the mean value theorem, the hypothesis of the mean value theorem? In other words, if the function differentiable and continuous, yes. If f prime of x equals 0 for all x, then then we might find down that then what f is what? F is continuous and continuous and differentiable everywhere, at every point. At every point. Why? Because it's differentiable. Oh, by the way, one of the theorem which I mentioned, which I did not mention in section 1.9, this is actually section 1.8. 1.8. One of the theorem is this, which I really didn't mention, is this. I think this is something you should study. Here, study this, okay? Study this theorem. Let me just write this down. So the theorem is this. If f is differentiable at x equals a, then f is continuous at x equals a. This is not hard to understand graphically, but this is actually a theorem which is mentioned in section 1.8. Why don't you study this theorem? I usually prove this theorem, and this theorem right here is a very educational theorem. It's an educational theorem because it is not so hard, and you have to know all these definitions here. You know what? This is not in, this is not in section 1.8. Where is this theorem? You know what? Oh, sorry. Oh, undo? Oh, no, I'm trying to redo this. Okay, redo? So let me, here, this one is going to be, actually, let me cross it out. It's not section 1.8. You know what? Again, I'm not sure where this theorem shows up. I have to look it up. But anyway, this one is differentiable. If f is different, x equals a, then f is continuous. Obviously, it has the word differentiable here. We did not study differentiability in section 1.8. This must be in section chapter 2 point something, but I'm not sure where. Okay. So now we have this, and now what is this equal to? Now this function f is continuous and differentiable. It is continuous. It is differentiable. How do you know it's differentiable? Because it says f prime is 0, so that means it's differentiable. We even know the derivative. And then if it's differentiable, then it's continuous, according to this theorem right here. So we have all these things satisfied, and therefore we can now apply the mean value theorem. So apply the mean value theorem here. So we have this conditions met right here. Now, this is what? Mean value theorem can be applied to this function. So we now write it this way. F of p minus f of q over p minus q times p minus q. And so now what do we see? This is therefore equal to now f prime at c, and then times, and then p minus q. This is now what? For some c. C less than p less c, be the c between what? C between p and q. So this equation is true. So f of p minus f of q is equal to p minus q times p minus q. And that's the first fact right there. According to our mean value theorem, that is equal to f prime of c, not for any c, but for some c. Well, we don't know where that is. But if you look at this theorem here, if you look at this, the assumption, what is the assumption here? The assumption is that this f prime of x equals 0 for all x. Doesn't matter where the x is. So therefore, we conclude that this actually equal to 0. And then this is actually equal to 0. And then this is equal to 0, and 0 times something. So this is equal to 0 times, and then what? P minus Q. Obviously, P minus Q is not 0, and therefore the answer is this is equal to 0. So what we have shown is that f of P minus f of Q is actually what? Is actually 0. It can only be 0, according to the mean value theorem. So that is the end of proof of part A, of 1A. And then 1B is actually a variation of 1B is a variation of 1A. So if you can handle proof of 1B, then you can. Why don't you try this? Try this 1B, okay? It's very easy. 1B is actually following from exactly from 1A. It's almost the same proof. Okay, so but you know what? I say that they're all easy, but then I'm not going to say that they're really easy. They're really short. What I really mean was they're all short. All of these they're very short proofs. But of course you have to know what to prove. So that will be the hard part. If you know what to prove, then it will take a minute or two, that's it. But if you don't know what to prove, then you don't know what's going on here. So the problem is a logical problem. It is not a calculation problem. So it's not much calculation here. But the extent that the logic has to go through very well. You have to write the assumption, you have to say what you're trying to show and what the assumption is, and then the progression, everything has to show a logical argument. The logical flow of the procedure is critical here. Not just putting the mean value here, that doesn't do anything. The logic has to work. If you look at the proof of this here, we start by saying that let P is not Q. That's the starting point. If let's say skip this part out here, if I just skip this part, if I skip this part, and then if I skip this right here, and then just show this part right here, will that show anything? And the answer is no, it doesn't. If you just have this part and don't have these parts right here, then it's not clear what you're doing, and therefore your argument will not be acceptable. Not clear. What is the P and what is the Q, and what is the P and Q doing here? We have no idea what the P and the Q is. So you cannot do this kind of thing. Many students, this is what they give me. They just give me this. And they don't care what the P and the Q is. Just say P is anything, Q is anything. No, can't say that. What happens if P and Q are 0? Then you cannot divide this. See? So things always all go wrong. So you have to make this argument clear. Especially don't use any letters without defining them. Many of you, that's what you do. You started using A, you started using C, and use P and Q, and then you know what? You never define what they are. So do you mean that P and Q could be anything? If it's absolutely anything, then you don't have to say anything, but in this case you can. Because here you have to assume that P and Q are two X values, and P and Q are not the same. So that's an assumption. And this is what we are trying to show. So you have to state what you want to show. What you have to show, you have to say that. Okay? And now class, let's look at part of example theorem here. How about the Q? Let's look at this guy here. If f power of x is greater than 0 for all x, then you have to show that this f is increasing. If the derivative is positive all the time, is the function is increasing? So here basically what we're showing is this. The question is this: f prime is positive, then what? Then what? Then f is increasing. Is that true? Increasing? Let me write this in red. Is that true? Is that true? If f prime is positive all the time, then is it true? Then is f increasing?
You're monkey, right? Yeah, I thought so. It's so cool.
Do you think that makes sense? If f prime is positive, then does that mean that f is increasing? Yes or no? Yes, this is actually true. True. So now let's look at the reverse. If f is increasing, then can you conclude that f prime is positive? Can you say this is true? If f is increasing, can you show that f prime is greater to the 0? Can you say that is true? Then is this true?
Even with
False.
your
This is false. If f is increasing, f prime is positive. That is not always true, because in this case, what is true is this. True, f prime is either greater to the 0, greater or equal to 0, or f prime does not exist. One of them is true. This case. So we cannot conclude that f prime is 0. F prime is greater than 0 if it exists. Okay. Okay. Now you know what I want you to. So I want you to see for 2 here. So what I want you to do is try to prove 2. Try this and try this. As usual, okay? Usual. Let's see whether you can prove these 2 statements, okay? You do. Number 2 and number 3, they're very similar. And the proof is actually very similar to number 1a, which I just did over here. Very similar. But you have to formulate the proof. That's the hard part. Again, the hard part is that these proofs are very short. Very short. These are very short proofs. Very short. Very short proofs must formulate. Must formulate the proof. Must formulate. That is, you have to know. You have to know how to structure. You have to present. Must present correctly, basically. Must present the proof correctly. So you have to write the assumption, and you have to write the assumption. What that means is write the assumption and write the mathematical statement which you have to show, and then the third step is you show the statement. Okay? So we have an assumption. So basically 3 parts of the proof. We have the assumption. So what is the assumption? We have hypothesis. So we have to state the assumption. Assumption. Then what? State the conclusion. State the conclusion. Statement. State the mathematical statement. State the mathematical equation. Mathematical what? The mathematical equation or inequality or something else. That's what you do. And then what's the next one? And then the third step is now what? The third step is now to prove. Usually this is a procedure, 3-step procedure. Write the assumption clearly, and then write what you're trying to show clearly, and then you have to show the statement. Yes, that's how you organize it. Okay, now here let's look at example 1. Let f of x be greater than 2 for all x, and f of 3 is equal to 1. Show that f of 7 is actually greater than 7. When you actually look at the proof, when you look at the graph of this, it kind of looks like this. You have this here. F of 3 equals 1. That's 3. And 1. Now here, suddenly there's actually a point on 9 at 7. And then the point is 9 over here. And this is a point 3, 9. This is a point 7, 7, 9. It is actually the point 7, 9. Now it says that this is the point 7, 9. It says show that f of 7 is actually greater or equal to 9. That means the point is actually over here. And let me mark this point over here. The point is actually over here. So now we have the point here. And now what we are saying is we are now going to draw a curve like this, where every curve, where the slope at every line, the slope at every point must be greater or equal to 2. So if we go up with slope 2 like this, if you go the slope at 2, then you can see that as this point is moving forward to the right, the question is from here to here, it's moving 8 up. So from the point 1, 3, 1 to the point 7, 9, it is actually going at which is actually going up at the slope of 2. But it says here f prime of x equals 2 for all x. If that's the case, how can you show that this f of 7 is greater than f of 9? That makes a lot of sense if you look at the graph here. So what we need to do is show this. Okay, now here's the proof. I'm going to show you how this looks like. This is going to be what? This is going to be what? So in this case, what we'll show is we'll show just f of 7. That's okay. Okay, should I just show that f of 7? Okay, we'll show that f of 7 equal to this is f of 7, yeah, f of 7. So f of 7 is f of 7 minus f of 3, and then plus f of 3. Yeah, that's right. Actually, it's subtracted in this. By the way, in this case here, we want to apply the mean value here. Where do you want to apply the mean value here? 1, 2, apply. 1, 2, 1, 2. 1, 2, apply. Mean value theorem on one interval. On the function f. Mean value theorem to the function f to f on one interval. Can you tell me on what interval we are going to apply this mean value theorem on? So when you see a problem like example 1, we can see that we will be applying the mean value theorem to the function f. On what interval do you think we'll be applying this? We'll apply the mean value theorem. So whenever we apply the mean value theorem, the grammar is this: we need a function and we need an interval. We need an interval where we will apply the mean value theorem. On this case, on what interval do you think we will apply the mean value theorem? Can you guess?
3 and 7.
3 and 7? That's right, 3 and 7. Because those are the only two x values which are mentioned here. So we know that we will apply this here, that is not in there. Of course, we can apply the mean value theorem function f, because function f, it says here, f prime of f is already greater than 2. That means the function is differentiable and continuous. They tell me that it's greater than 2. All around means differentiable and continuous. So if you want to now apply the mean value theorem to the function f on this interval right here, then we have to come up with this form right here. This form right here, this form, which we have right here, this guy right here, we need this guy. And so what do we do? Well, we start with f of 7, and we have to show that this is at the end greater equal to 9, but in the middle, we have to apply the mean value theorem. And in order to apply the mean value theorem, we need to have this guy right here. So, but we don't have that form, so what do we do? We create that form. So this is now equal to, this is equal to now, what is equal to now this? This is now equal to f of 7 minus f of 3. So let me write f of 7 minus f of 3, and then divide by 4. This is actually 7 minus 3, which you can just write that as 4. And this is equal to what? This is equal to this, and then equal to this, and then times what? Times 4. Times 4. Of course, we have this right here. So in this case, we just artificially create that form. We don't have that form, but we want to apply that. So now what we say, this is now equal to, now we can say we can now apply the mean value. So MVT right here. MVT right here. MVT right here. And so what is that equal to? That will be now f prime at c somewhere. And then times, and then 4. So here what I'm saying is that there is a c somewhere between what? For some c between, or for some c, now not for every c, for some c between what? Between 3 and 7. How about this? Between on the interval 3 to 7. Maybe I can just write this. So c on the interval 3 to 7. So we get that. So it's true for that. But now when you look at this here, it says this is f prime of f is equal to greater or equal to all x. Note that this is what the theorem says. it is what? It is true for all x. For all x now, not for some x. And therefore we know, and this is the part number here. So this must be greater than 1. This must be, you know what? I actually forgot this f of 3. I need to write plus f of 3. And then what I needed was, let me erase this part right here, eraser. Let's do, I don't want that. I want to erase this part. I forgot to put that again. Sorry. There we go. F of 10. And then now all I need to do is write that, what? Plus f of 3. So we have this. I forgot to put that plus f of 3. And so now, what is this now? This is now therefore equal to, what is f of f plus c? That is greater than 2. And we have plus number here. So we know that that is actually greater or equal to 2 times 4. And then what? And then plus, what is f of 3? F of 3 is actually equal to 1. And so, now we can say that that is actually what? Is actually equal to 9. So we can say that that is actually equal to 9. And the proof is now over. What did it show? We have shown that this f of 7 is greater or equal to right here. It says here, let me see, greater or equal to right here, and greater or equal to, and then 9 right here. So we have proven the statement.
Yeah.
Show f of 7
Thank
is
you so
greater than 9.
much.
Show it right there. Okay. Now, you know what, since I don't have that much time here, so let me stop here. Example 2 is right here, and you have to show this statement right here. So every real number a and b. Assume that a and b are in radian units. Okay, these a and b are in radian units. We assume all numbers are radian units. Okay, in radian units. So let me write radian. Okay, why don't you try example 2, okay? So actually I was planning to cover a little bit more today, but again, I guess I barely managed to finish section 3.2. Well, I don't know when our test is going to be, but start from section 3.3, I think we can move a little bit faster, okay? So we'll try to move a little bit faster from section 3.2. I was going to go to decimals and anyway, do section 3.3, but okay, we'll stop here. Okay, so now what I would like to ask you to do is there's a quiz prepared for you. So you have to, all of you must take the quiz now. So quiz 6 now. Okay, now must take now. Okay, take quiz 6. Take quiz 6 now. Okay, right now. So you can take a small break and take the quiz, but it will be closed.